Welcome to Review Lecture 6.1, Magnetic Fields. Upon completion of this, you should be able to find the magnetic field vector B, determine the magnetic field of a bar magnet, calculate the magnetic force on a moving charged particle in a magnetic field, apply the right-hand rule for charges moving in a magnetic field, and also the left-hand rule. Magnetism and electricity. How do we get magnetism? Well, actually, magnetism comes from moving electric charge or current. Any moving charge or current produces its own magnetic field. Actually, this is the source of all magnetism so far as we know, because we have not yet discovered magnetic monopoles, and we'll talk more about that later. This is what produces electromagnets. You know those things in the junkyard that pick up the cars? That's an electromagnet. Now, the other way is alignment via exchange coupling of electron spins, but even this is still the motion of charges. This is what makes ferromagnetism, that's refrigerator magnets, possible. Each atom has moving charged particles called electrons, which generate magnetic fields. In most atoms, they cancel so that the material has no overall magnetic properties. In some atoms of the ferromagnetic kind, they can add when the atoms are aligned. This produces what we call permanent magnets. And permanent is a term that's loosely used. The protons and even the neutrons also generate magnetic fields, but they are very weak and their effects are swamped by the electrons' contribution. So moving charges are the source of all magnetic behavior. So we have a moving charge here. It's a positive charge. It's moving along its velocity v. We're interested in a point here, a distance r from this charge. We're interested in the magnetic field at this point right here. Okay, so we have the magnetic field of a charged particle q moving with velocity v is given by the Biot-Savart law. So the b of the moving charge equals mu 0 over 4 pi times qv sine theta over r squared. Mu naught is called the permittivity constant. It equals 4 pi times 10⁻⁷ Tesla meter per amp, or 1.257 times 10⁻⁶ Tesla meter per amp. The SI unit of the magnetic field strength is the Tesla, abbreviated as a capital T. 1 Tesla is 1 Newton per amp meter, or 10 to the 4th Gauss. Some typical magnetic field strength. The field source at the surface of the Earth is about half a Gauss. That's 5 times 10⁻⁵ Tesla. A refrigerator magnet is 5 times 10⁻³ Tesla. A laboratory magnet, 0.1 to 1 Tesla. A superconducting magnet, 10. But there are dead stars called magnetars that have magnetic field strengths of 100 million Tesla, which is pretty incredible, and you wouldn't want to be anywhere near those things. They'd rip the iron right out of your blood. Now, magnetic fields are created by moving charges. The magnetic field of a moving point charge is circular, centered on the moving charge. And this is a positive charge, and notice it's moving along here at its velocity v, and here's its magnetic field. Now, there's a right-hand rule for this to determine the direction of the magnetic field. For a positive charge, grab the velocity vector v with your right hand, with your thumb in the direction of v. The curl of your fingers points in the direction of b. For a negative charge, the magnetic field points in the opposite direction, or use the Carroll-Whistle patented left-hand rule, which actually does work. The right-hand rule for finding the direction of b due to moving positive charge is very similar to the rule used for a current-carrying wire. And we'll talk more about that later. A current is just a bunch of charges moving in the same direction, and their fields add by superposition. And of course, we consider all currents to be a flow of positive charges. Note that the component of B parallel to the line of motion is 0, so there's no component of B in the direction of the motion. So there's always a right angle between B and V. Now, actually, it is a relative motion that counts. If you're moving along with a moving charge, you observe only the electric field of the charge because it's not moving relative to your reference frame. You will observe a magnetic field generated by the charge only if the charge is moving relative to you. This is relativity, and the notion that a moving charge generates a magnetic field is a step toward electromagnetic radiation, which is pretty much the rest of this course. Now, look, we're going to compare electric and magnetic fields. Electric fields are created by any charge. Charge comes in two flavors, positive and negative. Opposites attract and likes repel. A single charge can exist in isolation. The simplest form is one positive charge or one negative charge. The electric field at a point is determined by putting a stationary test particle of charge at that point and measuring the electric force on the particle. So E equals F over Q. A magnetic field is created by any charge that is moving relative to the observer. It comes in two flavors called poles, North Pole and South Pole. Opposites attract and likes repel. Poles never exist independently. We have never found an isolated pole, which would be called a monopole. If you have a North Pole, you always have a South Pole. All magnets have an equal number of north and south poles. The simplest form is one magnet with one north and one south. For this reason, we can't just use the stationary test charge method to define a magnetic field. Instead, we have to fire a moving charge into a magnetic field and measure what happens to it. So we're going to fire a small test charge in the magnetic field so that there's a relative motion between the charge and the magnetic field. A moving charge creates its own magnetic field, which reacts to the external magnetic field, producing a force on the moving particle. We measure the relative velocity v, the force Fb on charge q. And we do this over and over again. You'll find that the magnitude of the force Fb is the maximum when the angle phi between v and b is 90 degrees. Fb max equals qvb. Now that suggests a sine function because sine of 90 is 1. So we're going to rearrange that and include the effect of the angle phi between v and b to get the magnitude. B equals Fb divided by QV sine phi. Now the absolute value signs on this are there to remind us not to use the sign on the charge to determine the sign on force. You should use the right-hand rule to do that. We'll explain that in a minute. So Q is the particle charge, P is the angle between the direction of the velocity and magnetic field. And the units on this, of course, is a Tesla. The units of magnetic field strength of the Tesla, 1 Newton per Coulomb meter per second. That is 10 to the 4th Gauss. We will use a right-hand rule, and we'll talk about that later to determine the direction. For combined electric and magnetic fields, you add the forces just like any other vectors via superposition. So we're going to rearrange this and include the effect of the angle phi between V and B, and we've just done that. B equals Fb over QV sine phi. And of course, we rearrange this now to find the force on a moving charge particle. So Fb equals QVB sine phi. And of course, the direction is determined by the right-hand rule. For the calculus savvy, that is the Physics 222 students, the calculus-based physics students, we can summarize all of these results with the following vector equation using the cross product because cross product is associated with sine. So Fb equals QV cross B. For combined E and B fields, again, Physics 222, we have the Lorentz force law. F equals Fe plus Fb or QE plus QV cross B. Now E, these F's, V, and B are all vectors. Now, the right-hand rule. This is my favorite variation. I've been collecting right-hand rules for years. And so far, on this particular one, I've found about 4 right-hand rules and a couple of other variations. So the right-hand rule tells you to use your right hand. You point your index finger in the direction of the positive charge motion, V, or the conventional current. And a conventional current is a motion of positive charges. And the index finger starts with an I, and so does the symbol for current. It's an I. It makes it easy to remember. You point your middle finger in the direction of the magnetic field B, M for middle and M for magnetic. Your thumb then points in the direction of the force, and a force is a thrust on the particle, and that's Fb. So thumb for thrust. This works for positive charges and for conventional, which is the current is defined by Benjamin Franklin. For negative charges, the force points in the opposite direction, or you use your left hand. And as far as I know, I'm the only one who does that, and it works every time. The magnetic force is always perpendicular to the particle's motion. The magnetic force never has a component parallel to the velocity vector. Thus, it cannot change the particle's speed or kinetic energy. The magnetic force does no work on the particle. The magnetic force can only change the direction of the velocity or travel. This picture shows a chamber filled with liquid hydrogen immersed in a strong uniform magnetic field directed out of the image plane toward you. An incoming gamma ray, which is the path shown by the arrow, transforms via E equals mc squared into an electron and positron pair, in other words, a matter-antimatter pair, and knocks an electron out of the hydrogen atom. The positron, which has a positive charge, experiences a force directed to the left by the right-hand rule and circles clockwise in the field. The electron, which has a negative charge, experiences a force directed to the right and circles counterclockwise in the field. If you want to do this by the right and left-hand rule, we'll start with a positron, which is a positive charge. You use the right hand for the positive charge. The initial velocity of the positron when it's created is down the page. So your index finger should be pointing down the page. Your middle finger, which is your magnetic finger, should be pointing out of the page. Your thumb points to the left. That is the direction of the force on that particle at the instant of its creation. And we'll explain later why it spirals in the clockwise direction. For the negative charge, you use your left hand. Your index finger is still pointing down the page. Your middle finger is still pointing out of the page, but now your thumb points to the right. And that is the direction of the force on that particle at the instant it's created, which is right here. That causes the particle to deflect to the right and spiral counterclockwise. And we'll explain the spiraling later. We can represent magnetic fields with field lines, just as we did for electric fields, and similar rules apply. The direction of the tangent to a magnetic field line at any point gives the direction of the magnetic field at that point. So here's a tangent, here's the magnetic field line. This is the direction of magnetic field at point P. For this one, at Q, it's here. The spacing of the lines represents the magnitude of B. The magnetic field is stronger when the lines are closer together, like at point B, and they're weaker here at point Q, where they're further apart. Magnetic field lines always form closed loops. So in a bar magnet, magnetic field lines come out of the North Pole, loop through space, and enter the South Pole of the magnet and continue through the magnet back to the North Pole. So they always form closed loops. So the closed field lines enter one end of the magnet here and exit the other end. So the end of the magnet from which the field lines emerge is called the North Pole of the magnet. The other end where the field lines enter the magnet is called the South Pole. Because a magnet has two poles, it's said to be a magnetic dipole. Di stands for two. Opposite magnetic poles attract each other, and like magnetic poles repel each other. Now here's a picture made by sprinkling iron filings around a magnet. And you can see the filings line up to show the magnetic field lines around the outside of the magnet. However, they don't show the field lines inside the magnet. For that, this diagram suffices. They come out of the North Pole, circle through space, enter the South Pole, and continue through the magnet back to the North Pole. They always form closed loops. All magnets are dipoles, having a North and a South Pole. Cutting a magnet in half or in any other way produces two new magnets, each with a North Pole and a South Pole. The simplest magnet has two poles, one north and one south. Complicated ones like the sun can have millions of poles, always with an equal number of North Poles and South Poles. So if the sun has 1 million North Poles, it's got exactly 1 million South Poles. We have never yet found a magnetic monopole. Now, why do we call them North and South? Well, the Earth's magnetic field is similar to that of a bar magnet. It's generated by the currents in the Earth's molten outer iron core, and iron is a conductor. It's a fluid, and the Earth rotates rapidly. So the Earth is basically a huge electromagnetic generator, and we'll explain a little bit later when we talk about generators. Okay, we've been exploiting the fact that magnets, in which the naturally occurring ones are called lodestones, have been used to determine direction since the Chinese discovered this many hundreds of years ago. Back then, of course, we did not know how this worked. We called the end of the magnet that was attracted to the Earth's geographic North Pole in the Arctic a north-seeking pole. When we started analyzing magnetic fields, we kept the term North Pole, probably to avoid confusion. Yeah, sure. So the Earth's north geographic pole, which is under the Arctic, is really the south magnetic pole because the north-seeking ends of magnets are attracted to it because opposites attract. Yes, it's confusing, but there it is, and nobody's going to change it now. Now, we have to have some way of showing in two-dimensional space something three-dimensional that's coming at us or going away from us. So we're going to show this type of thing for directions on arrows. It's going to be sort of a standard thing for that. When you have something coming at you out of the page, such as this force that's coming at you out of the page, they show the tip of an arrow pointing toward you from the page. The dot is the arrow tip. Sometimes it's in a circle, sometimes it's a dot without a circle. The force F would then be pointed out of the page at you, and of course the color doesn't mean anything. When you have something away from you into the page, it is shown as a fletching of an arrow pointing away from you into the page. The X, which is the arrow fletching, that's the feathers on the back end of the arrow, is either in a circle or it's just an X without a circle. The magnetic field here would be pointing into the page away from you. The color is insignificant. So here's an example. We have a magnetic force on a moving proton. A uniform magnetic field with a magnitude of 1.2 millitesla is directed vertically upward through the volume of a laboratory chamber, shown pointing out of the page directly at you. See these little dots? That means the magnetic field's pointing at you out of the page. A proton with kinetic energy of 5.3 MeV enters the chamber, moving from south to north. That, of course, is up the page here. What is the magnitude and direction of the force on the proton? Well, the first thing you want to do is write down the knowns. The knowns is the magnetic field is 1.2 millitesla up the page. Q is 1.6 times 10 to minus 19th coulombs. That's a charge. Kinetic energy is 5.3 MeV. We're going to call V as positive to the north. The mass is 1.67 times 10 to minus 27 kilograms for proton. Phi is 90 degrees because of the angle here between V and B. And of course, then we need to know FB. The physics of this is a charged particle moving in a magnetic field. The formula for physics 222, folks, is FB equals QV cross B, and that will reduce for everybody to FB equals QVB sine phi. Kinetic energy is 1/2 mv squared. So at this point, we apply the right-hand rule because it's a positive particle. You have the middle finger, which is your magnetic finger, pointing up out of the page. Your index, which is the current of particle motion, points up the page to the north. Your thumb, which is the thrust or force finger, points to the right or to the east, and that's shown right here. Now we're going to solve for V. V equals the square root of the quantity 2ek divided by m, where ek is the kinetic energy, and m, of course, is the mass. FB is QVB sine phi, or QVB times sine of 90, of course, sine of 90 is 1. So that equals QB times the square root of the quantity 2ek over m. So FB then is Q of 1.6 times 10 to minus 19 coulombs, times your magnetic field of 1.2 times 10 to minus 3 Tesla, times the square root of the quantity 2 times Ek, which is 5.3 MeV, divided by the mass of the proton, which is 1.67 times 10 to minus 27 kilograms. This is the units conversion to get the MeV into joules. So there's 1.6 times 10 to minus 19 joules per 1 MeV. FB comes out to be 6.1 times 10 to minus 15 newtons to the east. Here's an example of a moving negative charge in a magnetic field. An electron experiences the greatest force as it travels at a speed of 2 times 10 to the 6 meters per second south in a magnetic field. The force is out of the page and of magnitude 3 times 10 to minus 12 newtons. What is the magnitude and direction of the magnetic field? So here's the velocity down south, drive that as south, and we have FB coming at you out of the page shown by this dot. Write down the knowns. V equals 2 times 10 to the 6 meters per second south. FB is 3 times 10 to minus 12 newtons up. Q is 1.6 times 10 to minus 19 coulombs, and we want to know B. The physics of this is a charged negative particle moving in a magnetic field. Now, you can use the right-hand rule or the left-hand rule. I prefer the left hand because otherwise then I don't have to remember to reverse the force. So you point your thumb out of the page. Okay, the thumb is the force. The index finger, which is the motion of the charge, is pointing down the page, and that's south. So your middle finger points west. That's the direction of the magnetic field, and that's shown here. So FB then becomes QVB sine phi. The maximum force, which is what they asked for, occurs when phi is 90 degrees. So the sine of phi becomes 1. So B equals FB divided by QV sine phi. And then that becomes 3 times 10 to minus 12 newtons for FB divided by Q, which is 1.6 times 10 to minus 19 coulombs, times 2 times 10 to the 6 meters per second. And of course, that is V. And of course, the sine of phi is 1. So B is 9.4 Tesla to the west. Okay, this slide regards a circulating charged particle. In other words, I promised you I would explain why a charged particle circulates in a magnetic field. So a beam of positron is projected into a chamber by a positron gun. Their velocity is perpendicular to the magnetic field. The positrons will enter the field with a speed v and move in a region of uniform magnetic field B. Now the magnetic field is shown, correct, is shown into the page, so there's meanings to these little X's. A magnetic force FB equals QV cross B for physics 222, or FB equals QVB sine phi continuously deflects the positrons. Since V is perpendicular to B, this deflection causes positrons to follow a circular path. They're positrons, so you're going to use the right-hand rule. The magnetic field, which is your middle finger, see these little X's, is directed into the page. So your middle finger should be pointing into the page. V, I'm going to use this side because it's easiest on my hand to do. Your index finger, V, is pointing up the page at that instant. Your thumb, F, is toward the center of the circle. Notice as you keep rotating this around, okay, as this particle deflects, it'll constantly have a force directed toward the center of the circle. That provides the centripetal force which bends the path into a circle. It does not change the kinetic energy or speed of the particle. It does change the direction. The particle then becomes trapped in the magnetic field and circles. Newton's second law, summation forces equals ma. The centripetal acceleration AC equals v squared over r. Combining QVB equals mv squared over r. We can solve this for the radius r of the circle. R equals mv over qb. The period t is just going to be 2 pi r over v. And that's how long it takes for it to go around once. It'll be in seconds. So period equals 2 pi m over qb. The frequency, which is how many times per second, or hertz, is 1 over the period. Frequency would be qb over 2 pi m. Now we can convert this to radians. So v equals r omega. Angular speed would be radians per second, would be qb over m. The period t and the frequency f are independent of the speed v. All particles of the same mass in the same magnetic field complete a circle in the same time. The radius r is proportional to speed v and mass m, and inversely proportional to the magnetic field strength b. High-speed particles have a larger orbital radius, which makes sense. Massive particles also have a larger orbit. That also makes sense. Higher magnetic field strength means a tighter orbit. That also makes sense. Now, what happens in the more general case where the particle is not injected perpendicular to the magnetic field? So typically a charged particle will not enter a magnetic field exactly perpendicular to the magnetic field's direction. So then we had to break this up into components. So we break them up into parallel components and perpendicular components. So here's the magnetic field. Here is the particle's velocity here. So here it is. Okay, so that's the initial point here. So the parallel component, which is this one, is going to be V cosine phi. Phi is this angle here between B and V. And this determines the pitch of the helical path about the direction of the field vector. P equals T times V parallel. So that is 2 pi mv cosine phi divided by QB. Now the pitch is how far this particle advances in this direction each time it goes around one time. So it's sort of like when you have a screw, okay, like a wood screw, and you're screwing into a piece of wood. If you turn that one turn, it's going to advance, get deeper into the wood by the pitch of the screw. The perpendicular component V perpendicular equals V sine phi. That determines the radius of the path. R equals mv sine phi divided by QB. So this means the particles spiral along and around a magnetic field line. Now the sun bathes the solar system in a streaming plasma bath of charged particles called the solar wind. Any planet with a strong magnetic field, that includes the Earth, Jupiter, Saturn, Uranus, and Neptune, can capture these particles which spiral along the magnetic field lines of the planet. The particles will enter the atmosphere near the magnetic poles and interact with the rarefied gases there. The gases are excited by this interaction and glow like the gas inside a fluorescent light. So here they are trapped in the magnetic field lines, and they enter where the magnetic field lines enter and leave the poles. And that causes the gases up in the upper atmosphere to get excited and glow. This ghostly glow is what we call the aurora. It is a sign that our magnetic field is protecting us from the sun. Now, the sun's solar wind would actually strip our atmosphere if it weren't for our magnetic field. That actually happened to Venus and to Mars. It caused Venus's atmosphere to turn into a hell of carbon dioxide, and Mars basically is too cold and too thin. Venus is too hot and Mars is too cold. Because their lack of a strong magnetic field allowed the solar wind to damage and destroy their atmospheres. So our magnetic field is absolutely essential for us to retain our atmosphere. It also protects us from other dangerous high-energy particles from interstellar space, which would damage our DNA. So here's an example of a mass spectrometer. A mass spectrometer can be used to measure the mass of an ion of mass M to be measured, and charge Q is produced in source S, which is down here. The initially stationary ion is accelerated by the electric field due to a potential difference V. The ion enters the separator chamber in which a uniform magnetic field B is perpendicular to the path of the ion. The magnetic field is represented by the dots pointing at you out of the page. A wide detector lines the bottom of the chamber, and the magnetic field causes the ion to move in a semicircle and thus strike the detector. Suppose that B equals 80 millitesla, V equals 1,000 volts, and the ions of charge Q of 1.6022 times 10 to minus 19 coulombs strike the detector at a point that lies X equals 1.6254 meters from where the ions enter the chamber. What is the mass M of the individual particles in atomic mass units U? Okay, so the first thing you do is write down the knowns and unknowns. V equals 1,000 volts, Q equals 1.6022 times 10 to minus 19 coulombs, X is 1.6254 meters. What is mass? We also know that B is 80 times 10 to the minus 3 Tesla. Notice everything should be converted to SI units. The physics of this is a moving charged particle in a magnetic field. The particle's velocity is perpendicular to the magnetic field, which will give us the maximum force, and we also need the energy law. So at this point, we need the formulas. R equals mv over qb, and also R equals x over 2. And we also know the kinetic energy plus the potential energy equals 0. The kinetic energy is 1/2 mv squared. The potential energy is just the electrical potential of the particle, and that's minus qv. So now we can start playing with the algebra. mv over qb equals x over 2. We can solve that for v. v equals qb x over 2m. And at 1/2 mv squared minus qv equals 0. And we can plug and chug until we find that m equals b squared q x squared over 8v. Now we can plug numbers in. We have, for our magnetic field, we have 80 times 10 to minus 3 Tesla, and of course that's going to be squared. Our charge is 1.6022 times 10 to minus 19 coulombs. Our x, which will be squared, is 1.6254 meters. divided by the 8 times the V of 1,000 volts times the units conversion down here to convert from kilograms to atomic mass units. One atomic mass unit is 1.6605 times 10 to the minus 27 kilograms. So the mass is 203.93 atomic mass units. You look this up, this would either be thallium-204 or lead-204. How could you determine the difference? Probably through chemical means. A positive charge enters a uniform magnetic field as shown. What is the direction of the magnetic force? This is a positive charge, so it's a right-hand rule thing. And the magnetic field is directed into the page. So your middle finger should be directed into the page. Motion, your index finger should be directed up the page. That's V. And the magnetic force is to the left. The middle finger, which is the magnetic finger, is into the page. The index, which is the motion or current, is up the page. The thumb, which is the thrust or force, points to the left. A positive charge enters a uniform magnetic field as shown. What is the direction of the magnetic force? And what would be the direction of the magnetic force be for the negative one? The answer is up the page for the positive particle. The middle finger, which is the magnetic field, is into the page. The index finger, which is the motion of the particle, or V, is to the right. The thumb, which is the force, points up the page, so up the page. Now, for the down the page for the negative particle, it will be opposite to the force on the positive particle, or use the left-hand rule. The middle finger, which is the magnetic field, points into the page. The index finger, which is the velocity, points to the right. The thumb, which is the force, points down the page. So point down the page. A positive charge enters a uniform magnetic field as shown. What is the direction of the magnetic force? And what would the direction of the magnetic force be for a negative particle? Now, is into the page for a positive charge. Use the right-hand rule because it's a positive charge. The middle finger, which is the magnetic field, points to the right. The index finger, which is V, points up the page. The thumb, which is the force, points into the page. So the force is into the page. It'll be out of the page for the negative charge, which is the opposite to the positive particle. Or you can use the left-hand rule. The middle finger, which is a magnetic field, points to the right. The index finger, which is V, points up the page. The thumb, which is the force, points out of the page. So out of the page for the negative charge. A positive charge enters a uniform magnetic field as shown. What is the direction of the magnetic force? And what would the direction of the magnetic force be for a negative particle? Now notice the motion and the magnetic field are in the same direction. That means the force is going to be 0. Okay, your middle finger and index finger are parallel to each other. When you do the right-hand rule or the left-hand rule, and you see the middle finger and the index finger being parallel to each other, the force is 0. And it doesn't matter whether it's a negative or positive charge. It'll work for either hand. A beam of atoms enters a magnetic field region from the left. What path will the atoms follow? The atoms are not ions. And what kind of charge will follow path number 3? And what about path number 1? Well, if they're not ions, they're going to be going in a straight line, so that's path number 2. What kind of charge will follow path number 3? And what about path number 1? Well, I just assumed it was positive. So I said, okay, I'm going to use the right-hand rule because it's a positive charge. Magnetic field, which is my middle finger, is directed into the page. The velocity of the particle is going to the right, so that's my index finger. If it's a positive charge, my thumb is pointing up the page. So that means number 1 is positive. And the opposite of that would be the negative charge, and that's number 3, down the page. And by the way, don't worry about whether this bends or not. This would actually bend and start to spiral, but I didn't have any way of bending this. So a proton beam enters into a magnetic field as shown. What is the direction of the magnetic field be? Okay, it is minus Z into the page. It's a proton, so use the right-hand rule. The thumb is a force, which is up the page. The index, which is V, is to the right. The middle finger, which is the magnetic field, is minus Z into the page. For electrons, the magnetic field will be out of the page. For neutral atoms, you could not tell because there's no force to cause a deflection or a curve. A proton enters a uniform magnetic field that is perpendicular to the proton's velocity. What happens to the kinetic energy of the proton? The kinetic energy does not change. The magnetic field also does not do any work on the proton. So kinetic energy stays the same, and there's no because the force is always perpendicular to the velocity and the displacement. What direction would the magnetic field have to have if a beam of electrons moving to the right goes undeflected through this region where there's a uniform electric field pointing vertically upward? Well, the first thing you want to remember is that electrons love to swim upstream. So they're not going to go up, they're going to go down. Now you have to figure out what kind of magnetic field you need to make sure the electrons don't go down. So in other words, you need a force directed upward. It turns out it's going to be out of a page. Without a magnetic field, the electrons are going to feel an electric force downward. In order to compensate, the magnetic force has to point upward. Use the right-hand rule, okay, or what I would suggest you do is use the left-hand rule. You want the magnetic force to point upward. Your velocity is pointing to the right, so your index finger is pointing to the right. You want the magnetic force to point upward. Your thumb has to be going up. Your middle finger is coming out of the page. That's the magnetic field. Okay, a horizontal wire carries a current is in a vertical magnetic field. What is the direction of the force on the wire? Well, you can treat the current as a flow of positive charges. Use the right-hand rule for the conventional current, which is the same as for a positive charge. Index, which is the current, points to the right. Middle finger, which is the magnetic field, points up the page. The thumb, which is the force, points out of the page. And by the way, force is always perpendicular to the plane defined by B and V, or in this case, I. So F must not lie in the plane of the page since I and B are both in the plane of the page. A vertical wire carries a current as a vertical magnetic field. What is the direction of force on the wire? It's 0. When the direction of I is in the direction of V, in other words, they're parallel. So your index finger and your middle finger are going to be parallel to each other. Force is 0. What is the direction of the magnetic field at a point P directly below a point at the center of the magnet? The numbered arrows represent various directions. Direction 1 is to the right. Direction 2 is to the left. Direction 3 is upward toward the center of the magnet. Direction 4 is downward away from the center of the magnet. 5 is toward you, and 6 is away from you. Well, the magnetic field lines are come out of the North Pole, go past point P in the direction of 1, and enter the South Pole. So the answer to that is number 1. A negatively charged particle travels parallel to magnetic field lines within a region of space. Which one of the following statements concerning the force exerted on the particle is true? The force has a magnitude of 0 newtons. The particle is traveling parallel to the magnetic field, so no force. In other words, your index finger and your magnetic finger are lying next to each other and they're parallel, so your thumb should be basically 0. You've lost your thumb. Positively charged particle is stationary in a constant magnetic field within a region of space. Which one of the following statements concerning the particle is true? There will be no force on the particle because it's a relative motion between the particle and the magnetic field that counts. So the magnetic force is 0. No force means no acceleration. The particle will just sit there. Two particles of the same mass enter a magnetic field with the same speed and follow the path shown. Which particle has the greater charge? And what is the sign on these charges? R equals mv divided by qb. So q is proportional to 1 over r. So number 2 is larger. What is the sign of these charges? By the right-hand rule, they're both positive. Both of them are being deflected to the left here. So what you want to do is put the middle magnetic finger, your middle finger, into the page. Your index finger, which is the initial velocity, is up the page. The force on both those particles is to the left, so that means they're both positive. Two positively charged particles are moving in circles with a uniform magnetic field. Particle A has a radius that's 1/2 that of particle B. Which of the following statements concerning these particles is true? Both particles have the same mass. Velocity of particle A is smaller than that of particle B, but they both have the same frequency. So R equals mv divided by qb, so R is proportional to V. F equals qb over 2 pi m. F is independent of V. Thank you.